Today, I'll be presenting on my literature review topic, lightweight authentication methods for IoT devices. As IoT devices become more common in areas such as smart homes and healthcare, security has become increasingly important. However, the challenge is that many IoT devices are highly constrained. This is why lightweight authentication is needed. A lightweight authentication method is defined as being able to maintain strong security while keeping computational costs and communication overhead as low as possible. In this presentation, I will review three lightweight authentication methods discussed in my paper. First, let us look at hashing. Hashing is one of the most fundamental cryptographic tools used for data integrity and authentication. A hash function takes an input of any length and produces a fixed length output called a digest. This digest acts like a fingerprint of the original message. Even if only one bit of the input changes, the digest changes completely. Also, a good cryptographic hash function is designed to be one-way, meaning it's computationally infeasible to recover the original input from the digest. In a basic authentication process, the sender computes a hash of the message and sends both the message and the digest. The receiver then computes the hash again using the received message and compares it with the transmitted digest. If both match, the message is considered authentic and untampered with. The main benefit of hashing is its efficiency. Hashing requires relatively simple operations and is much cheaper than public key cryptography. It also produces a small fixed-size output, which reduces communication overhead. This makes hashing highly suitable for constrained IoT devices. On the other hand, hashing usually depends on shared secrets, which means the communicating parties must already share key material beforehand. This can make large-scale deployment and key management more difficult. Next, I will discuss elliptic curve cryptography, or ECC. In ECC-based authentication, each device has its own public key and private key. When the device wants to authenticate itself, the verifier sends a fresh challenge, usually a nonce. The device then signs this nonce together with some context, such as the device ID, using its private key. The verifier checks the signature using the device's public key. If the signature is valid, the verifier can confirm that the device is genuine and possesses the correct private key. Because the nonce is fresh every time, replay attacks are prevented. Through this, ECC is able to achieve security comparable to older public key systems like RSA, but with much shorter keys. For example, a 256-bit ECC key can provide security roughly comparable to a 3072-bit RSA key. The key benefit of ECC is that it provides strong identity assurance without requiring every device to share the same secret. Since each device has its own key pair, ECC supports better scalability and more flexible trust management. This makes it suitable for larger and more dynamic systems, such as smart city infrastructure. However, compared to hashing, ECC requires more computation and therefore more energy. This means it may still be too expensive for the most constrained devices if used continuously. The third method is physically unclonable functions, or PUFs. Unlike hashing and ECC, PUF is based on hardware. A PUF takes advantage of tiny manufacturing variations in silicon, which naturally makes each chip physically unique. These unique physical variations allow a device to generate a response to a given challenge. Since even chips built from the same design cannot be made exactly identical, the response is very difficult to clone. In practice, the device receives a challenge, applies it to its PUF, and produces a response based on its physical characteristics. The main benefit of PUFs is hardware-rooted security, because the secret is derived from the physical device rather than being stored permanently. PUFs reduce the risk of memory extraction attacks. This is especially valuable for devices deployed in hostile or unintended environments. However, its biggest issue is reliability. Since PUF outputs can be noisy, extra error correction and helper data are needed to reconstruct a stable secret. This adds design complexity. Now, the main conclusion of my paper is that there is no universally best lightweight authentication method. The most suitable method depends on the system's requirements. Hashing is best for efficiency, ECC is best for scalability and strong identity verification. Finally, PUFs are best for hardware-based trust and protection against key extraction. Typically, a combination of methods work best. For example, a system may use ECC during initial authentication, then switch to hash-based authentication for regular low-cost communication. Thank you.